Hello and welcome to this video on determining if a transformation is an isomorphism. So in this video I'm going to define what is an isomorphism, or what does it mean for a transformation to be an isomorphism between two vector spaces, and also what does it mean for two vector spaces to be isomorphic to each other. Then I'll go over several examples where I'm given a transformation and then I'm trying to determine whether or not that transformation is one of these isomorphisms. Then finally I have, in the last part of the video, I have an important result that you should know about isomorphisms and isomorphic finite dimensional vector spaces, and a last example or two related to that result. All right. So beginning here, I'm talking about what is an isomorphism. So a transformation, T, from vector space V to a vector space W is called an isomorphism if the following two things are true, right? And both of these have to be true. One, well actually it's four things if you really look at it. Number one, T has to be a linear transformation or a matrix transformation. Remember, any matrix transformation was also a linear transformation and vice versa. And what did this mean, right? What did it mean for T to be linear? That meant that these two properties had to be true, had to hold, the additivity property and homogeneity property. All right, so for all vectors in the domain V, right, the domain, say vectors u and v from domain V, and all scalars R, the image of u plus v under T would be equal to the image of u under T plus the image of v under T, right? Or T of u plus v equals T of u plus T of v. Right, so they would say with this property that T, the transformation preserves vector addition. And then homogeneity is, T of R times U is equal to R times T of U, again where R is a scalar. And this homogeneity property, they'd say that the transformation T preserves scalar multiplication between the sets. Okay. And I've talked in other videos about, linear transformations. I'm not going to dig too much into that. Equivalently, if you wanted to just show both of these kind of at the same time, which I'm not going to do here, but if you'd like to, equivalently you could show that T preserves linear combinations. It preserves right. In other words, show that T of say AU plus BV, right? There's a linear combination of vectors U and V from the domain, and A and B, or let's say A and B are scalars, right? Is that equivalent to A times T of U plus B times T of V, right? If you can show this, one line, this really shows both of these at the same time. But like I said, I'm going to do each one separately. I prefer it. Nothing wrong with this, right? This is just my personal preference to show both additivity and homogeneity separately. Okay, so in order for T to be an isomorphism, it's got to preserve linear combinations, right? So any linear combination in V will map to a corresponding linear combination of vectors in W, right? Another way to say this is that they kind of have the same structure when they're isomorphic. All right, well, we'll get to that in a second. All right. So 1, T is linear. Great. And in order for a transformation to be an isomorphism, T has to be an invertible transformation. That means, if you recall inverses maybe from pre-calculus or algebra, remember the inverse is just simply reverse the mapping. So like if a vector v went to a vector w in T, then the inverse vector w would go to vector v. And when I say invertible, I mean that the inverse is also a legitimate transformation, a legitimate function. So I would like every vector in W to go to map to only one vector in V. So the way that's going to be happening, the only way T is invertible then is if the following two hold, and I just put up videos recently on these. If you've been following, T must be 1-to-1. Right? This must be 1-to-1, because if there were two different vectors in V that went to the same vector in W, then the inverse, when I reverse the mapping, would not be a function or a legitimate transformation, because you'd have a vector in W mapping to two different or three different or four, more than one element of V, and that's not part of a definition of a function, right? Or again, a legitimate transformation. Also, in order for T to be considered invertible, T must also, on top of being 1-to-1, must also be onto, meaning every vector in W is an output of T. So every vector of W is mapped to or has a non-empty pre-image. Again, the reason why this is tied into T being invertible is because if I were to reverse it, then every vector in W would have an output in the inverse, right? Because if it wasn't onto, right, if it weren't onto, then there'd be some vectors in W that don't get mapped to by T. So when you reverse, that means there'd be some vectors in W that don't map backwards, that don't map to V. And that's not part of, again, the definition of a function or a transformation. A transformation assigns every value from the domain to a value from the codomain. Right. So an isomorphism is a transformation that is both linear and invertible. You have these two additivity and homogeneity properties holding, and you have the transformation is 1-to-1 and onto. Alright, so when I'm asked to check, determine if a transformation is an isomorphism, I first go through the linearity stuff. Right? I check to see if it's a linear transformation first. Alright, because if it is a linear transformation, then I can write it as a matrix transformation, right, and look at the standard matrix. And then I can use the standard matrix to very easily tell if the transformation is 1-to-1 and onto. Right, I've gotten into that in previous videos. And if the transformation's not linear, well, then there's no way that it's going to be an isomorphism. Alright, and then one other definition associated with this. If an isomorphism exists between vector spaces V and W, so that means you can find a transformation between V and W that's both linear and invertible, then we say that V and W are isomorphic to each other. Right. Another way to think about that too is if V and W are isomorphic, that would mean that V and W have a similar structure. Meaning, again, remember that whole concept of isomorphisms, preserving linear combinations. Linear combinations in V would correspond to linear combinations in W. The additive identity in V would correspond to the additive identity in W. And what we're going to see later is a very important result, and this is what I'm saying, how they have a similar structure. A basis, if you have a set of basis vectors of V, those will map to basis vectors of W. A basis of V will correspond to a basis of W. So building blocks for V will be, in a relationship with building blocks for W. All right, if they are isomorphic to each other. If you can find an isomorphism between them, then yes, they'll have this similar structure to them. Okay. So now for the next few examples, several examples, I have this, just the same instructions for each one of them. I'm given a transformation between two vector spaces that you're hopefully familiar with by now. And I'm asked to determine whether the given transformation is an isomorphism. All right. Now, the linearity part. And so here T is a transformation from that, P2, that set of polynomials of degree 2 or less, to R3, right, the three-dimensional Euclidean space. And here's the rule, right? It takes a polynomial from degree 2 and just sends it to a vector from R3. So the first question is, if I'm asked is T an isomorphism between P2 and R3? Is T a linear transformation? Right. Now, you could check for the additivity. Again, I put up a video before on checking to see or determining if a transformation is linear. So hopefully go watch that or look for some other videos on that, determining whether a transformation is linear or not. Now I could go through and check the additivity and homogeneity properties or that linear combination property separately, right? But I could do those here. But one thing I'm noticing is that if you were to think of these in terms of the remember in previous videos when we had vector spaces that weren't Euclidean, you could translate it to work so that you were working with the coordinates of these vectors relative to a standard basis. All right, so remember the standard basis for P2 was just a set with x squared, x, and 1 in it. And again, you could put it in the other order. But I'll put it in this order and stick to this order for this example for this video. So I could translate this here to T of, and then have my input, instead of be a vector from P2, be the coordinate vector for this relative to this basis. So let's call this basis B, by the way. B is this x squared, x, and 1. We say I have A times x squared, so A is the first component. B times the second basis vector is the second component. C times 1. So these are the coordinates of this vector from R2 relative to the standard basis for R2. And then this side here, now this is Euclidean space, right? So I don't need to change things to coordinates for Euclidean spaces because they're already written as a column vector. All right, that's the only reason I translate other vector spaces into coordinates, is so I get a bunch of column vectors that I'm used to. And what I'm noticing here is that this can be expressed as a matrix times the input vector. Let me show you how. Right. So it'll actually be a 3 by 3, and down the first column the coefficients of A, which are 1, 1, and 0 in those components. then the coefficients of b, which are 1, -2, and 0, and then the coefficients of c, which are 0, 0, and 1, and then multiply by, the input vector. Right? And since I can do this, right, since I can write the output as a matrix times the very input vector, right, that input coordinate vector, we're seeing here that t is a matrix transformation. Right, I can express the output as a matrix times the input vector. Therefore, t must be linear, right? T is a linear transformation. Wonderful. All right, so that's part one. The answer is yes. Now again, you didn't have to do this. You could have checked, is that additivity property true? Is that homogeneity property true? Right? And if both of those were true for vectors and scalars, you would have shown that t was linear. Okay, but like I said, if you can see it, if you can see how to write the transformation as a matrix transformation, where the output is a matrix times the input vector, then you've got a linear transformation. All right. All right. So t is linear. Then part two of this question, is t an isomorphism? The question is t, invertible? Or, again, is it 1-to-1 and onto? 1-to-1 and onto. All right. Well, just I did a video on this also, right, showing using the reason I wrote this as a matrix transformation is to make this part a little easier for me. Asking this question is basically the same as asking, is the standard matrix invertible? This is asking pretty much the same question as, is the standard matrix, because again, if it is linear, it'll have a standard matrix associated with it. So is the standard matrix invertible? All right, now you could answer that in a bunch of ways. Remember, here I have a square matrix, so it may or may not have an inverse, and I could just find the determinant of this matrix, right? So we could do this. I could say, let's call this matrix A here. What is the determinant of matrix A? And you see how it would be easy just to do cofactor expansion down the third row or even the third column, because there's just a bunch of zeros. Then I'd have the number 1, times the cofactor for this, which it's a third row, third column. That's an even position. So it would be multiplied by the determinant of this 2 by 2 up here, right, with the 1, 1, 1, -2, which would be -2 minus 1, be -3. This matrix has a determinant of -3, which is not 0. All right, so I have a square matrix, a square standard matrix for this transformation with a non-zero determinant. So that means A inverse or T inverse, right? If you're talking about the transformation, exists. Therefore, T is invertible. All right. Now, another way you could have done this. Was to take this matrix and put it in an echelon form, whether it be just regular echelon form, row echelon form, or reduced echelon form. And if all the columns were pivot columns, that implied you had 1-to-1, right? If all the columns were pivot columns, that means all the columns of the matrix were independent, and if that's the case, you're going to have a one-to-one transformation. And to check for onto, again, you put this matrix into an echelon form. If it has a row of zeros in it, then you're not onto. That means that the column vectors do not span the codomain. The range of t wouldn't be equal to R3 in this case. But if it doesn't have a row of zeros, then you were onto. And I'm hoping you can see that this, when you, I already told you the determinant wasn't 0. Alright, so when you put this into reduced echelon form, it would just be the 3x3 identity matrix. So every column would be a pivot column, and there wouldn't be any rows of zeros, so it would be one-to-one, check, and onto. Alright, so yes indeed, t is invertible. So therefore, we have shown here that t is a linear transformation. We have shown that t is invertible. So this particular transformation is what they call an isomorphism. So t is an isomorphism. All right, and then on top of that, since I have shown you here, here's a transformation from P2 to R3 that is both linear and invertible. There's an isomorphism between P2 and R3. They would also say after this that P2 and R3 are isomorphic. All right. So, meaning they have similar structures. All right. Now I'm going to point something out here that we'll get into later as well. What are the dimensions of these spaces? All right, remember the dimension of P2 was 3. And the dimension, because again, remember the standard basis had just 3 vectors in it, that x squared, x, and 1. And the dimension of R3 was also 3. So, I know it's only one example, but what we're going to see later is that spaces that have the same dimension are going to be isomorphic. That means you can find a transformation between the two that's both linear and invertible. We'll see that later. All right, now the next one. Now here's another transformation between the same two sets, same two vector spaces, R3 and P2, right, just in the other order. Now remember in the last example, I said R3 and P2 were isomorphic. That's because we could show a transformation between them that was both linear and invertible, an isomorphism. Now this example is just to show you that just because two vector spaces are isomorphic, that does not mean that every transformation between them is an isomorphism. Right? When you say two spaces are isomorphic, that means there is at least one transformation out there between them that's an isomorphism. Not every transformation between them will be an isomorphism, like I'll show you here. And I'm going to tell you right now, here's a transformation from R3 to P2. T of, a vector from R3 with components A, B, C goes to this, polynomial of degree 2 or less with a plus 1 times x squared plus bx plus c. I'm going to tell you right now that T is not linear. Let me show you why. I'll just give you a very quick counterexample. So here's a vector from R3, say 1, 2, 3. Right, this belongs to R3. And let's pick another vector here. Say 3, negative 1, 4. Why not? Alright, so both of these belong to R3, correct? And they are clearly not the same. Alright, they are clearly not the same vector. So let's see, what is t applied to the sum of those two? Well, I'm checking to see if the additivity property holds for just this pair of vectors. Alright, so if I add these two first, I'd get the vector. Again, we're using standard operations here, nothing crazy, just the usual vector addition and scalar multiplication. 1 plus 3 is 4, 2 plus negative 1 is 1, 3 plus 4 is 7. Alright. And then according to the rule for t, if I apply the rule for t to this vector, I'd have 5x squared, right, 4 plus 1, plus x plus 7. Alright. Now let's see if I get the same thing if I apply t to each of these separately and then add them, right, instead of adding first. So what's t of 1, 2, 3? And then add to that t of 3, negative 1, 4. Alright, well, t of 1, 2, 3 would be, again, 1 plus 1, so 2x squared plus 2x plus 3 plus, and then t of 3, negative 1, 4 would be 4x squared, 3 plus 1, and then minus x plus 4. Putting these together, combining like terms, you'd have 6x squared, and then plus x plus 7. And look, these are not the same because of those lead terms, right? That's 5x squared, that's 6x squared. These are not equal. Alright, so the additivity property fails. Alright, so t of u plus v is not equal to t of u plus t of v for all u and v in the domain. And that's bad, right? So t is not linear, meaning that this particular transformation between R3 and P2 is not an isomorphism. Alright, and again, I wanted to bring this particular example up to make this point. Alright, we saw in the first example. We saw in the first example that P2 and R3, there is an isomorphism between them. This particular t here, right? This transformation is an isomorphism between P2 and P3. So therefore, P2 and P3 are isomorphic because you can find at least one transformation. There it is. You can find at least one transformation between them that's linear and invertible. But here's a transformation between the same two sets that's not an isomorphism, but that doesn't mean they're not isomorphic, right? They're still isomorphic. The definition was that you can find at least one. So that's the key point I wanted to make here. So just because two set R3 and P2 were isomorphic, that doesn't mean that every transformation between them is an isomorphism. Right, that doesn't mean that every transformation between them is an isomorphism. as I just showed you here, these are isomorphic vector spaces. I showed you that in the first example. But here is a transformation between them that's not an isomorphism. Right. Let me go back one more time to the definition of isomorphic. Right. The key word here is an. If an isomorphism exists between the vector spaces v and w, then v and w are said to be isomorphic to each other. So you only need to find one transformation between them. That's linear and invertible. Right. Now if you find one that isn't, that doesn't mean anything. Right? They could still be isomorphic vector spaces. Just because you found a transformation that wasn't an isomorphism doesn't mean that there isn't one out there that is an isomorphism, right? So you got to be careful with that. Just because you're seeing a transformation that isn't an isomorphism, that doesn't mean that those vector spaces aren't isomorphic, right? There may be a transformation out there that is an isomorphism. And like I said, later I'll give you the conditions that'll show you for certain whether or not two spaces are isomorphic, and it's really about their dimension. Right, you saw that P2 and R3, right? Both of those have dimension of 3. And we're going to see later that only vector spaces with the same dimension will be isomorphic. All right. Okay, another example. All right, so this time I have a transformation from R 2 by 2 to P1, right? This is the set of polynomials of degree 1 or less. And here's the transformation, here's the rule, right? I take my input is a matrix, 2 by 2 matrix with real entries A, B, C, D. And my output is some polynomial of degree 1 or less, so some number times x plus a constant, right? So this A plus B times x plus, and then C plus D for the constant term. Now, based on what I said a minute ago, right, look at these vector spaces. We have R2 by 2. Now, hopefully you recall that the dimension of that set of 2 by 2 matrices was 4, right? 2 times 2. And the dimension of the set of polynomials of degree 1 or less was 2. So these do not have, this set here and this set here, these vector spaces, these do not have the same dimension. So there's no way they can be isomorphic. So in that case, right, since these two are not the same dimension, I know for certain that this is not going to be an isomorphism. Again, only spaces with the same dimension we will see will be able to be isomorphic, could possibly have an isomorphism between them. Right? But let's figure it out, right? As I haven't stated that yet, I'm just pointing that out. Right? Okay. So first, is T linear? Now again, I'm going to do this thing with the matrix stuff, but if you could go through work. Is the additivity property true? Is the homogeneity property true? You can do those on your own. I'm going to do that stuff with the matrix. All right. So remember the standard basis for R2 by 2. Was those 2 by 2 matrices with 1 in one position and 0 everywhere else, and there were 4 of them, right? Thus the dimension 4, right? All right, and then the standard, I'll call this B, and the standard basis for the codomain was just x and 1, right, for the P1. So I translate this stuff to coordinates, All right, we'll do translate everything to coordinate vectors with respect to these two bases. So I have T of, and then this matrix with A, B, C, D here is, A of this first plus B of this second plus C of the third plus D of the fourth. So it has a coordinate vector A, B, C, D. Right, it's a 4x1 coordinate vector. This is with respect to basis B. And this is equal to, and then again this side here I can write in terms of coordinates as a column vector. I have A plus B times X plus C plus D times 1. So it's a 2x1 with A plus B times X. So A plus B as the first coordinate, and C plus D times 1, C plus D as the second coordinate. Right? And this is with respect to basis C. Right? Basis C. Right, and then like earlier, I can see how to write. I can see how to write this as a matrix times the input vector. If you can write the output as a matrix times the input vector, you have a matrix transformation and therefore a linear transformation. And if you can't see how to do it, then go back and check the additivity property and homogeneity property, because maybe one of those fails, and if one of those fails, perhaps you could find a counterexample. I'm just going to put the coefficients. Oops, shouldn't be so big. Matrix, it'll be a 2x4 matrix. Coefficients of A, we have 1 then 0. Coefficients of B, got 1 then 0 again. Coefficients of C, 0 then 1. Coefficients of D, 0 then 1. There's that 2x4 matrix multiplied by the input vector A, B, C, D. And if you multiply these two matrices, you get this one back, and it's a matrix times the input vector. So I do have a matrix transformation implying that it is a linear. T is linear. All right. Notice that this is not a square matrix, so you can't invert it. If the standard matrix has no inverse, then T is not invertible. It won't be 1-to-1, or it won't be onto, I don't know, one of those. Now, it's going to be onto, right? This is in reduced echelon form, actually. Right? This standard matrix is in reduced row echelon form already. Right? The lead non-zeros are 1s with zeros below and above them. So you see I have no rows of zeros. So number 2, is T so linear, yes. Is T invertible? Well, again, the answer is no. It's not a square matrix. A matrix that's not square won't have an inverse, but we'll see that in a second here with these other things. But is it invertible? Well, looking at these, there aren't any rows of zeros in this echelon form here, reduced echelon form. So T is onto. All right, that's good. All right, that means that every polynomial in P1 is an output. Means the range of T is P1, but T is not 1-to-1. Again, you can see that from the matrix here. Look at the pivot positions. There's a pivot, there's a pivot. See how only the first and third columns are pivot columns, and then you have 2 columns that aren't pivot columns. That tells me that not every vector, not every column in the original matrix, in the standard matrix here, is independent, which will again imply to me that T is not 1-to-1. All right, again, go back to look at my video on 1-to-1-ness, or proving that a transformation is 1-to-1 to get more details on that. So is T invertible? Nope, it is not. And again, very simply, I could have just looked at this standard matrix here and said, this is not a square matrix, so it doesn't have an inverse. T can't be invertible. All right. Yeah, so this particular, and really any transformation between these two would not be an isomorphism, again, because they have different dimensions. But we're seeing that this particular this particular transformation is not an isomorphism between R2 by 2 and P1. Okay. Alrighty, moving on. Got another example. So again, you can pretty quickly look at the dimensions and tell. So here I have a transformation from the set of real numbers to the set of complex numbers. Now the set of real numbers had dimension 1, right? The dimension of the real, a basis for R is just a set with the number 1 in it, right? So the dimension of the reals is 1. Now the dimension of the complex numbers, we've seen this before, right? The standard basis for the complex numbers were the numbers 1 and I, right? Because every complex number can be written as a real times 1 plus a real times I. So that has dimension 2, the complex numbers. And these two vector spaces don't have the same dimension. So right away I can say this is not going to be an isomorphism, because there's no possible way that these are isomorphic spaces. They don't have the same dimension. So if they don't have the same dimension, every transformation between them is not going to be linear and invertible at the same time. Right? It could be one, could be the other, but not both. Right? So let's check that out. Now, again, I'm going to translate these to coordinates. So I mean, t of a is just going to stay. I'll just say, a will stay as a. It's just a real number. Right? Again, anything in the Euclidean spaces, I'm going to just keep that way. Right? They're already set up as column vectors, or in this case, just a number. R1 was just numbers. But this I'm going to put coordinates relative to the standard basis. And the standard basis for the complex numbers, like I said earlier, had the numbers 1 and I in it. So the first coordinate would be 3a times 1, 3a. And the second coordinate, positive 5a times I, so 5a. Right, I get this 2 by 1 coordinate matrix. And then I'll put let's call this basis C or something. This is relative to basis C, right, for the complex numbers. And I can tell easily that this can be written as a matrix times the input, right? This is just the matrix. It's a 2 by 1 matrix with 3 and 5 in it, just the coefficients of a times a, right? I can very easily write this as a matrix times the input, right? So again, we have a matrix transformation implying that T is a linear transformation. Now, again, if you don't see it, go back and check the additivity property, the homogeneity property, and see if those work out. They should. All right. But either way is fine, right? Showing that it's a matrix transformation or showing that those additivity and homogeneity properties hold. All right, but then if you take this it's not a square. This is not a square matrix, right? This is a 2 by 1 matrix, 2 rows, 1 column. So it doesn't have an inverse. So right away I'm saying T is again not invertible. Right, and again, that's because the standard matrix isn't a square. So it definitely can't be invertible. Now, if it was a square, that doesn't mean it is, right? Right? Just because a matrix is square doesn't mean it has an inverse, right? You've seen that before as well too, right? I'm assuming you have, right? If you've gotten this far in material. The standard matrix is not square, so it couldn't have an inverse, right? So this is not a homomorphism. An isomorphism. Homomorphism. You abstract algebra people out there know what I'm talking about. All right. But again, if you didn't check that, if you wanted to put this standard matrix into echelon form or reduced row echelon form, right, this one would be very simple. It would just be this matrix here All right, multiply that by a third, and then times -5 plus the second row. So we'd see that t is 1-to-1, right? If you look at this, the only column in it is a pivot column. Obviously, a single column vector is going to be independent, right? So definitely 1-to-1 this transformation is. But look, there's a row made up entirely of zeros. So t is not onto. All right, that means that there are some complex numbers here that wouldn't be mapped to. Like for instance, 3 plus 6i wouldn't be mapped to. 3 plus 5i would if I just plug in 1 for a, but 3 plus 6i wouldn't be an output ever. Right? So definitely not onto, therefore not invertible, therefore, t is not an isomorphism. It's linear but not invertible. Right? Okay. All right. Then before we get into the final part of the video on some how isomorphic vector spaces have similar structures, just got one more example here. All right, so this time got T as a transformation from the set of 2x2 matrices to the set of the polynomials of degree 3 or less. Remember, the dimension of R 2x2 is 4, right? 2 times 2. The dimension of P3 is also 4. All right. Now this does not mean that this is an isomorphism. All right. This means that the sets are isomorphic. Right. This will tell me that R2x2 and P3 are isomorphic. They have the same dimension. That means there is at least one transformation between them that's an isomorphism. That doesn't mean that this one is. Right? It doesn't mean that every transformation between them is an isomorphism. It just means that there is one out there that is. Okay. All right, so we got to check. All right. So again, if the dimensions are different, you can say right away, not an isomorphism. It can't be. If the dimensions are the same, then you have to check. All right, you have to check for linearity and all that. All right. So I'm going to call the standard basis. We know the standard basis for these. This is those 2x2 matrices with 1 in one position and zeros and everywhere else. And this has x cubed, x squared, x, and 1. So I'm going to call the standard basis for R 2x2. I'm not going to write it out. I'm just going to call it something. I'm going to call that B. And the standard basis for P3, I'm going to call that C. Right? Again, you should know what those sets are by now. These are familiar, hopefully, to you by now. All right, so I'm going to do is I'm going to change this input and this output to coordinate vectors. So this is T of, and then we have A, B, C, D, and this is with respect to the basis for R 2x2, right? And the output here, ax cubed plus bx squared plus cx plus d, that's a times x cubed, b times x squared, c times x, d times 1. So it's just a, b, c, d, with respect to c, with respect to the standard basis for P3. This is pretty much like the identity, right? The identity transformation where every vector gets sent to itself. So yes, I can easily write this as a matrix. It's just a 4x4 identity matrix, right? The coefficients of A, 1, 0, 0, 0. Coefficients of B, coefficients of C, coefficients of D. All right, I can write it as a matrix times the input vector. So definitely a linear. So T is linear because I can write it as, the output is a matrix times the input. right, as a matrix transformation. And now, this is a square matrix. But remember, just because a matrix is square doesn't mean it has an inverse. Well, this is the identity matrix, so I mean, the inverse of the identity matrix is the identity matrix. So T is invertible, right? It would be 1 to 1, it would be onto. Right, because look, every single column has a pivot. So all columns here are independent, meaning that T is 1 to 1. And there aren't any rows of zeros. So that means that this particular set of column vectors spans, R4, which would correspond to the dimension, this has the same dimension as P3. So this would be onto, right? The range of T is P3. So putting these together, T is an isomorphism. But you have to check, right, when they have the same dimension. Like I said a second ago, right? Just because the spaces have the same dimension doesn't mean the transformation is an isomorphism. All right, so the spaces are isomorphic, but the transformation that you're looking at may not be an isomorphism. Just like I showed you earlier, the very first two examples I showed you demonstrated that. Right, I had between P2 and R3, right? P2 and R3, those both had dimension 3, and I showed you how one was an isomorphism and one was not. You got to check. All right, now here's a nice result you're going to want to remember about isomorphic vector spaces and isomorphisms, these really special transformations. So here's a key result. Isomorphisms preserve bases. This is what I meant about earlier about how these vector spaces that are isomorphic have very similar structures. So suppose we have a transformation from V to W that is an isomorphism between V and W, right? So it's a linear invertible transformation. Suppose B is composed of vectors from V, say V1, V2, all the way up to Vn. Say this set of n vectors is a basis for vector space V, a basis for the domain. Well, in order to, if you plugged all these into T and got outputs, T of V1, T of V2, T of V3, T of Vn, you'd get these n vectors. If it's truly an isomorphism, if it is linear and invertible, this resulting set with T of V1, T of V2, T of Vn, and so on, this set will be a basis for the codomain. So that's what I meant by earlier saying that isomorphic spaces have similar structures. A basis for the domain will correspond to a basis for the codomain. Right? Remember what it means to be a basis. That means that every vector in V, every vector in the domain can be written as a linear combination of these vectors, and these vectors are independent. And the vectors that they correspond to, the vectors that they map to, would also be independent, and every vector in the codomain can be written as a linear combination of those outputs. All right, so bases correspond to bases in isomorphisms, in isomorphic sets, vector spaces. Right, and that's a beautiful thing. Right? And that also implies to me that if the dimension of the vector space V is n, then the dimension of the codomain would have to be the same. Right, so that's why this implies that isomorphic vector spaces have the same dimension. All right, and I have just a couple of examples here. Those Pn, the set of polynomials of degree n or less. This has dimension n plus 1. So that would be isomorphic to the Euclidean space with n plus 1 components, Rn plus 1. Right, both have dimension n plus 1. As we saw earlier, P2 was isomorphic to R3. Right? R m by n, right? This is the set of m by n matrices. Remember, the dimension of this set was m times n. So this would be isomorphic to any other vector space with m times n as its dimension. So say Rmn, Rmn, right, m times n up here. The Euclidean space with m times n components. Both of them have dimension m times n. So R 2 by 3, the set of 2 by 3 matrices, would be isomorphic to R6, right? Euclidean space with 6. Or P5, because that has dimension 6 as well. Right? Any vector spaces with the same dimension are isomorphic, meaning you should be able to find an isomorphism between them. Again, that doesn't mean that every transformation between them is an isomorphism, but it means you can find one, right? At least one transformation between them. That's an isomorphism. But something that's both linear and invertible. All right, and not only does it work for this concept, this statement work for vector spaces that we've been looking at here, but also for any subspaces, right? Remember, a subspace of a vector space is also a vector space, right? So it has a dimension, and then any other vector space with that same dimension would be isomorphic to the given subspace. So I have an example of that on the next page. Right. And this is my last example. I'm just going to go over one example demonstrating this. So, here V is the set of all 2 by 2 diagonal matrices. So this is a subset of that R 2 by 2, right? The set of 2 by 2 matrices with real entries. This is actually a subspace, and here's another way to describe this set, right? Remember, what diagonal matrices are matrices that have only entries, down the main diagonal, and then 0 everywhere else. So some number A, 0, and then 0, and then some number B, A and B down the main diagonal, where A and B are any real numbers. All right, so this was a vector space, right? It's just it only but it doesn't have dimension 4. It doesn't have dimension 4 because here's a basis right here. Right? A basis for V is the 2 by 2 matrix with 1 in the upper left corner, and then the other one is with the matrix with the 1 in the lower right corner, and that's it. Because those are the only positions that actually can take on any values, right? So the dimension of V is 2. I'll write that up here. Also, W here is R2. We know that the dimension of R2 is 2. All right, so you see these spaces have the same dimension. So that means V, right, the set of all 2 by 2 diagonal matrices is isomorphic to R2. Right? And here is an isomorphism between them, right? And I've already told you it's an isomorphism, right? I've already told you. You can go through and check again. But here is this is an isomorphism. This is a linear invertible transformation between the set of all 2 by 2 diagonal matrices and R2. So here it is. I take a 2 by 2 diagonal matrix, I plug it in, and I get a vector from R2 back, where just simply that first row first column entry is the first component, and the second row the other diagonal entry is the second component. It's that simple. Alright, so here's a basis for V. Now this would be like the standard basis for V. It's the very simplest building blocks for V. If I were to plug these in, I should then get a basis for R2. And let's see. So let's find the images, find the outputs of these vectors, right, these matrices. Alright, so I'm going to find the images. So what's T of the first basis vector for V, that 1, 0, 0, 0? If I plug this in here, I'm just replacing A with 1 and B with 0, so I'd have the vector 1, 0. And what's the image of the other basis vector, T of 0, 0, 0, 1? Again, apply T to this, that's just replacing A with 0 and B with 1, so I'd have 0, 1. So what I'm getting here is the set of vectors 1, 0, and 0, 1. And we already know this. This is the standard basis for R2. But this is indeed a basis for R2. As was said on the previous page. If I have an isomorphism, which this is, I've already told you this is, you can check it again. If I have an isomorphism between two vector spaces, like this one is, if you know a basis for the domain, just plug in those vectors. Their outputs, their images, will give you a basis for the codomain. Any basis in the domain should correspond to a basis in the codomain in an isomorphism between two vector spaces. So same example, right? Here's a different one. So that was just with the standard bases, Here's a different one. Right? So same isomorphism, right? The same transformation here, the same isomorphism T. Same, the domain is a set of all 2 by 2 diagonal matrices still. The codomain is still R2. But here's another basis for V, right? And you can check this out on your own. These are not scalar, there's two vectors here, two matrices. They're not scalar multiples of each other, so they're independent. And you could check on your own that every vector in here, every vector in V can be written as a linear combination of these two. You can check that as well. All right. These do span V. All right. So here's another basis for V with the 2, 0, 0, 5, negative 1, 0, 0, 7, these 2 by 2 matrices. So again, if I want to find a basis for R2, another basis for R2, I just take this basis for V and plug it into my isomorphism, and it should give me a basis for the codomain, a basis for R2. All right, so let's do that. Let's find the images of these basis vectors. So what's the value of T at the vector 2, 0, 0, 5? That's just replacing A with 2 and B with 5, so I get the vector 2, 5. All right, and then what's the image of the other basis vector, negative 1, 0, 0, 7? That's just replacing A with negative 1 and B with 7. So I get the vector negative 1, 7. All right, so this set with vectors 2, 5 and the vector negative 1, 7, this should be a basis for the codomain. This is a basis for the codomain, right? Because this is an isomorphism, right? An isomorphism should send the vectors from a basis for the domain to the vectors for a basis of the codomain. And you can double check if you want. I'm not going to go through and test this, but you can see that they're independent. First of all, there's only 2 of them and they're not scalar multiples of each other, so definitely independent. And then you can go through and check, does this set of 2 vectors span R2, right? Is every vector in R2 a linear combination of these two? And it should be the case, yes. All right, I'm not going to go through and verify that right now. I just know that it's going to happen. Okay, but what I just showed you, these last 2 examples, this should be happening for every isomorphism you come across. All right, so if you come across a transformation that is an isomorphism, and you know a basis for the domain, you just plug those vectors in and you'll get corresponding vectors that form a basis for the codomain. Right. Again, these isomorphic vector spaces have very similar structures. Right. Wonderful. All right. So again, an isomorphism is just a transformation that is both linear and invertible. So the linear, right, you can either show that it's a matrix transformation, right, show that the output can be written as a matrix multiplied by the input vector, or go and show that the additivity and homogeneity properties hold. And it's invertible, right, meaning you have to show that it's 1-to-1, show that it's onto, right. Now the way you show those, again, if you've shown it's linear, then you can find the standard matrix for it, and put it in some echelon form. If every column is independent, or if every column is a pivot column, it's 1-to-1. If not, it's not 1-to-1. And if every row is not full of zeros, not all zeros, then it spans the the codomain it's onto. If it's not, if there is a row of zeros and it doesn't span, it's not onto. Right? It's really that simple. Right? I mean, it sounds like a lot. It is a lot. There's a lot to check here. And then once you have an isomorphism, that means you have two vector spaces with the same dimension, and also with a very similar structure. Right? Bases in one correspond to bases of the other, right? As we just saw in this last pages. Right? So I hope you have fun practicing problems involving isomorphisms, and thank you very much for watching.